go ahead and get started. I had you down for an entry ticket, but we don't really have time for that, so I think I'm going to, I'm not going to assign that. We will have an exit ticket, but it's not until Monday. Your only assignment today then would be the worksheet that you picked up with your notes. Today we are exploring exponential growth. That means we're looking for patterns and diagrams. We're learning what a basic exponential equation looks like, the parts of it that we can use to write it, and what it looks like when it's graphed. And we're going to kind of compare that to what a linear, the things that we know about a linear equation. We know a linear equation. One of the forms that we use the most is slope-intercept form, so y equals mx plus b, where m is the rate of change, and b is that initial value, that starting amount. So that, when we graph that, that's a line, right? Linear equation, root word line. Now, exponential equation, the form that we're going to use for the exponential equation is going to be y equals a times b to the x power. So this is what makes it an exponential equation. There is a variable in the exponent. If there's a variable in the exponent, it's an exponential equation. It's not going to look like a line when it's graphed. A is the initial value in an exponential equation. B is the growth rate, which is really it's the kind of the rate of change version of an exponential equation. It's not a constant rate of change though, so we're going to talk about what that looks like. So you should have written at least this down, preferably both of those things. No? Anywhere, somewhere, right below the title, where I have it. Writing it right there, bud. I'm getting ready to change the page now, but that's where we're writing. All right. We're going to look at our first example. This is recorded, so if you didn't get it, if you started writing it late, you can come back and get it. All right. Look at the table. We're looking for patterns, similarities, and differences. What do you notice about the tables? Identify 3 similarities and/or differences. We're not going to write anything down right now. I just want you to look at the tables and see what you notice. How are they the same? How are they different? What do you notice? How are they the same, Ezra?
So the X is going up by number, Y follows that pattern.
Okay. What do you notice, Kennedy?
The table 1 and 4 get divided by 8, 2 and 3 are getting multiplied by 0.2.
2 and 3?
2 and 3.
1, so table 1, you're adding 8 here, 8 here, 8 here, 8 here, true. 8 here, 8 here, 8 here, 8 here. I think table 3, what did you say was getting multiplied by 2? Added by 16. Anybody else? What do you notice, Mason? Something similar, something different.
What?
The table, the 4 tables. Lawson, do you notice anything?
Not really. Not that they all have them.
Not that they don't what?
Nothing that they all have them.
Okay. Well, they all have an X and a Y coordinate, right? These 3 tables start with 0. This one starts with 1. These X's go up by 2. All the other X's go up by 1. We can add 8 here to go up. Can we add a number for table 2 to go up? No. Can we add, we're adding 16, Kennedy said here, so 0 to 16, 16 to 32, 16 every time makes sense. Kennedy said we're adding 8 on here. So this is the only one that we can't add the same number to the y's to get the next number, right? Table 2 is an exponential function. How are we getting from 1 to 4, 4 to 16, 16 to 64, 64 to 256? Say it again. We're not squaring. What did you say, Ezra? Yeah. So 4 squared is 16, right? But 16 squared isn't 64. But 1 times 4 is 4. 4 times 4 is 16. So one thing, a couple of things. Table 1, X doesn't start at 0. Table 1, the inputs increase by more than 1. I don't care which things you put there. Put 2 things, whatever you thought of if you want. But this is the one I want us to really pay attention to. Table 2 doesn't have a constant rate of change. Remember, linear equations have a constant rate of change. The y's increase by the same amount as long as the x's are increasing by the same amount. So table 1, the x's increased by 2 every time, well, until we got to 15. But we can also check that rate of change. Remember, for a linear equation, y minus y divided by x minus x. And even though we went from 7 to 15 for our x's, if you find the rate of change or the slope of that table, then they would have a constant rate of change. Okay, so table 2 doesn't belong. Table 2 is not a linear relationship. The growth in that table is not linear. We're writing number 2. All right, caught up with me? All right, so we've got a series of figures to bottom left there. So just like we looked at the tables to find a pattern, we're going to look at these diagrams, these triangles to find a pattern. It says count the number of shaded triangles in each figure. So shaded are the darkened ones. So there is, how many triangles in figure 0? 1. So the white one pops out at me, but we're counting the dark one. So figure 1, there's 3 triangles. How many in figure 2? Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. So figure 2 looks like 3 of figure 1, right? And figure 3 looks like 3 of figure 2, right? So 1, 2, I don't even know how it would look at. I'm challenged with the spatial part of the geometry, but the math I can do. So I know if I count, that's 9, 9, 9. So I know there's 27 shaded triangles in that figure. So based on those 4 figures, what is the pattern? What's happening there? Multiplying by 3. So the y's are increasing by a factor of 3. They're going up by a factor of 3. So 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. So the pattern is increasing by a growth factor of 3, and I'm not going to make you write that, but it is the last result multiplied by 3 to get to the next. You will just write the first part there. And the growth factor we said on the first screen, that's our B, and we're writing an equation. So what would the 4th figure look like? There would be 81 triangles, right? And I don't really, somehow there would be 3 of these figure 3s in there, but I cannot picture it in my head. I'm just going to tell you. So there'll be 81 shaded triangles, and we're going to scratch that. Oh no, we're not going to write that. So figure 4, there would be 81 triangles. So if the pattern increases from one figure consecutively, 27 times 3 would give us 81. So if we plot these on the coordinate plane, so when you create a T-table like this or a chart, you're really creating ordered pairs. So we can plot these points on the coordinate plane. We're going to go from small numbers up to pretty big numbers, so we got to kind of adjust the increments on our Y and X axis. So on our Y axis, we're going up by 10. On our X axis, we're going to use 2 boxes for every one. As long as your increments on each axis are the same. So all the increments on Y are 10. All the increments of X, every one is 2 boxes. You're good. If we plot points over 0, up 1, and this is already plotted for you, but I'm going to review it. We're going to plot the next one. Over 1, up 3, so 1 is actually 2 boxes. And these aren't super exact, so between this line and this line is 10, so we're going to go up just a little bit. Over 2, up 9. Now 27 is almost to 30. We're going to over 3 and almost to 30. And then 4 is all the way up to 81. So over 4, all the way up. This line is 80, just barely above that would be 81. The exponential graph is always going to be a curve. You'll notice the difference between the dots. So these two, the growth between 0 and 1 is very little, right? Between 1 and 2, not much more. But as our x's increase, that growth between each increment of one x value increases a lot. So between 0 and 1, it only went up by 2. So between 3 and 4, it went up by, is that 54? So it went up by a lot, right? So as if we were to plot 81 times 3 would be 200 and something. So it would go up very off our chart, right? So this is characteristic of an exponential function. The difference between the small increments of the lower increments of x are closer together, and then as x's increase, and for our purposes, it's for compound growth financially. The interest in our investments are going to grow a lot more over time. So the equation here, what is the initial value, A? What is our starting value? It's 1. So y equals 1 times 3 to the x power. Anthony, did you write that already? You did? Because I'm getting ready to change it. You didn't? Okay. All right. I'm going to look at this diagram at the bottom. Count the number of endpoints, or the branches at the top in each figure. So that confused me. Endpoints, I get. Branches at the top, there's no branch here. But there is an endpoint here, right? There's one endpoint there. So the points on the outside are the endpoints. So there's 1 here, there's 2 here. For the second figure, the endpoints are here. The third figure, the endpoints are here. So figure 2, there's 4 endpoints. How many for figure 3? 8. So what is the pattern? What is the growth factor from figure 0? What is the growth factor? Times 2. 1 times 2. 2 times 2. 4 times 2. So the growth factor is going to be 2. We can say that it's doubling. That's another thing we should look for. If it tells us it's something that's doubling, tripling, quadrupling, we should know those are different factors. Doubling is a factor of 2, tripling a factor of 3, quadrupling a factor of 4. So figure 4 would have how many endpoints? Yes, 16. 16 endpoints. And the y's are increasing. That makes this a growth factor. Let's plot them. We'll use increments of 2 again on our x-axis, increments of 2 per box on our y-axis. So 0, 1, over 0, up 1, over 1, up 2. Are you guys graphing? Over 2, up 4, over 3, up 8, over 4, all the way up 16. So you can see how much more the dots, the points are spreading out as the x's get bigger. The y's are increasing at a much greater rate than the x's. Exponential, the graph of an exponential equation, if there's a growth factor, it's always going to be going up from left to right. Like a positive slope in a linear equation goes up from left to right. Starts low, goes high, because there's a growth rate. We should be able to recognize the growth rate in this equation. So the equation that represents this table, y equals our initial value of 1, our growth rate of 2. If you're given this equation, you should be able to tell me that 1 is your initial value. That's the starting y value. B is how much what we're multiplying our x values by. or our y values by, rather, to get the next y value. All right. Endpoints threw me off again. Endpoints here. I wanted to count these as endpoints. They're not endpoints. The only thing they count as endpoints are things that are on the outside. So there's 4, 8, 12, 16 endpoints, right? And so then only the ones on the outside here. So figure 1, there's 4 endpoints. Figure 2, 16 endpoints. Figure 3, there's 16 on each of those, so that's 64. So what is our factor? What is our growth factor here? What is the growth factor? DVM, do you know? What's happening? How are we going from 4 to 16, 16 to 64? What are we doing? Multiplying by what? 4 times 4. 4 times 4 is 16. 16 times 4 is 64. So our growth factor is 4. You could also describe it as quadrupling. So if B is greater than 1, then it's a growth factor. If B is less than 1, that means that the y's are decreasing. We're going to talk about that in a second. So how many endpoints would be on a figure 4 if it were drawn? Good. So 64 times 4 would be 256. It would be 256 endpoints. What would this equation be? What is A? So A is not here, right? But if we're multiplying by 4, as it increases, we could divide by 4 to get our 0, so that would be 1. So same pattern, initial value, the growth factor, x is always that exponent, so it's y equals the initial value times the factor it's growing by raised to the x coordinate. These are ordered pairs. Let's go ahead and plot them and graph them. So you're plotting the point over 0, up 1. I put increments of 25 here because we had to go all the way up to 256. So over 0, up 1 is going to be just barely above that bottom line. Remember, these are approximate. They do not have to be exact. 1, 4, over 1 and up 4, it's going to be just barely above that. 3, 64, so, 216. Over 2 and up 16, it's going to be a little over half of 25. Put it about right there. 3 and 64, so over 3, that's the x value, and 64 is between 50 and 75, about right there. And 4 and 256, it's going to go off the table or right to the edge of that table. That's about 6. You see how it looks like these points are about the same distance apart, and then all of a sudden it jumps. That is that exponential growth. The graph is always going to look like this curve, and it's always going to be going up left or right if the y's are increasing. Caught up with me? All right, so let's look at the area of the shaded region here. Figure 0 has an area of 1, so the entire square is shaded. Figure 1, what portion of that square is shaded? Half. figure 2 rather, 1 out of 4, right? Because you could split this into 2 equal parts, so that would be 1/4. Each of these quadrants, if we had 2 sections, this would be 1/8. So what is the pattern? It starts at 1, now it's at 1/2. Then it's at 1/4. So they're getting smaller now. This is an example of an exponential function with a decay factor, so that b is less than 1. So how do we get from 1 to 1/2? We are multiplying still. 1 times 1/2 is 1/2, right? If we multiply 1/2 times 1/2, we would get the 1/4. 1/4 times 1/2, so top times top, bottom times bottom, we get 1/8. So our decay factor is 1/2, or we could use a decimal. Usually we're going to use a decimal here. What portion of the whole box is going to be shaded in figure 4 if we were to draw it? Well, we're going to take that 1/8 and multiply by 1/2. So top times top is 1. 8 times 2, bottom times bottom is 16. So 1/16 of that box. So it would actually be, we would split this one in half, right? So that would be figure 4. You don't have to draw it, but we should know that 1 out of, there'd be, it has 16 boxes with 1 shaded in. Or just split in half like that. So the y's are going down, so this is decreasing. So our graph is not going to look the same. We are going to describe our growth rate as being reduced by half. You could say dividing by 2 times 1/2 is another way to say it. Our growth rate, or decay rate, our decay factor, decay rate, however you're going to say it, is 0.5. Our initial value is still 1. Does not have to be 1. We're just using very basic examples for these problems so you can understand just the basic format of the equation. So y equals the initial value of 1 times our decay factor of 0.5 raised to the x power. We are going to graph it, and this one's important because this one's going to look different than the other ones we've done. I numbered the y-axis as 1.0, 0.75. I don't know if you guys can see that. So 1.0 here, so 0, 1, over 0, up 1. Over 1, up a half, so 0.5 is the same as 1/2, right? Over 2, up a quarter, or 0.25. Over 3, up 1/8. We can put that on the calculator, but we know that it's going to be half of this, right? Over 4, up 1/16, it's going to be half again, so it's going to be about here. So if you draw that, if you sketch that graph now, you can see that now that curve is going down from left to right. So that is the difference between a decay function and a growth function. All right, so kind of to summarize, a linear equation, y looks like y equals 10 times x. It's in this format, y equals mx plus b, where the rate of change is 10. That means we're adding 10 to each y value, right? There's 10 here, 10 more is 20, 10 more is 30. If you graph that linear function, starts at 0, 0, then 1, 10, then 2, 20. It's a linear relationship. You graph it, it's a line. An exponential function, that x is always an exponent. It's y equals 3 raised to the x power. This is the basic format. The initial value times the growth or decay factor raised to the x power. In this case, b is 3. That means that each y value increases by a factor of 3. So if our first one is 3, we multiply by 3 to get the next one of 9. We multiply by 3 to get the next one of 27. If we plot these, this ordered pair would be 1, 3. This ordered pair would be 2, 9. This ordered pair would be 3, 27. So we plot them on our graph, and this is what you get. You get that curve going up from left to right. That growth factor is greater than 1, so we know our y's are increasing. You guys have a box that I don't have on my notes, so we're going to leave that one blank. So this is just kind of to summarize the difference between the linear function or equation and exponential function or equation. And that's basically what we just talked about. I don't think you have that one on yours. All right, and the last box on there, you don't have this table. So you just make yourself a little T table that says linear and exponential. If you don't know what I mean do this. All right, you're writing that on your notes. Kennedy, you with me? Writing that in your notes. One of the things you're going to have to be able to do on the test is you're going to have to be able to pick out linear versus exponential, or identify linear versus exponential functions. So we've got A through L. Which one is linear? Which ones are exponential? Anytime there's a variable in the exponent, it's exponential. So for A rather, y equals 2 to the x power, that's an exponential function. Does that make sense? See if you guys can categorize them. Look through and put the letters for all the linear equations here, all the exponential equations on the right, and then we'll check them. Topic in your backpack or on my desk. Your phone goes in your backpack. What do you think? So we already said A was exponential, right? What do you think about B? Is that exponential or linear? Mason, what do you think? Exponential or linear?
Exponential.
Yep. So remember, exponential is increased by a factor. So if you're multiplying each one by 7, that would be exponential. How about C? Y equals 9 to the x power. Is that exponential or linear? Sincere? C. Y equals 9 to the x power. It is. Very good. It's got x as the exponent. D. Y equals 2x. Is that exponential or linear, Mylan? Very good. What did you say?
I know, I'm lost. You said put the X.
plus 5 plus 5 plus 5. Would that be a linear relationship or an exponential? What do you think? Not exponential. So if it increases by adding the same amount, that's linear. F, y equals 1.05 raised to the x power. Would that be exponential or linear, Miana?
Exponential.
Yes. G, you add $50 to your account every month. Would that be a linear or exponential? What do you think, Zariah? Very good, linear. The value of an investment doubles every decade. What does it mean for something to double? Multiply by what? Whose music is on? So we can lose the privilege of those altogether. H would be exponential. I, how are the y's increasing? Are we adding the same amount or are we multiplying by something? So is I going to be exponential or linear? What is the growth factor? Times 5, times 5, times 5, right? How about J? Is that linear or exponential? How are the y's changing? Adding what? Adding 25 each time. That's linear.
Oh, I got the rest.
K.
Got it.
Times 10, times 10, times 10, right? And this graph is not a line. It is a curve. So we have learned that would be an exponential function that's increasing. It would have a growth rate of L. And so L is an exponential function. You've got about 4 minutes is all. You can scan and submit those notes. Kennedy, honey. What are you doing? What are you texting so much? Oh, your password. Okay, I get it. Makes sense. I thought you were texting.